Welcome to SS2 Technical Drawing, Term 2, Week 1. Last term we developed truncated prisms. Today we extend this skill to truncated cylinders. A truncated cylinder is a cylinder cut at an angle by a plane inclined to its base. The cut face is an ellipse. When we unfold the curved surface of the cylinder, it becomes a flat rectangle. But when the cylinder is truncated, the top edge of that rectangle becomes a wavy curve rather than a straight line, the curve that matches the elliptical cut. Development of truncated cylinders is examined by WAEC every year, and it combines skills from orthographic projection, true shape finding, and surface development. Sheet metal workers use this development to make offset pipe connectors, conical duct pieces, and exhaust pipe elbows. The curved surface of a right circular cylinder, when unrolled, becomes a flat rectangle. The weight of this rectangle is the stretch-out length, which equals the circumference of the base circle, pi times the diameter. For a cylinder of diameter 50 mm, the stretch-out length is pi times 50, which is approximately 157.1 mm. The height of the rectangle is the height of the cylinder. For a complete right cylinder, the development is a plane rectangle of width equal to the circumference and height equal to the cylinder height. When the cylinder is truncated, the top of the development is no longer a straight horizontal line but a curve that rises and falls according to the position of the cutting plane around the circumference. We must find the height at 12 equally spaced points around the cylinder to plot this curve accurately. Here is the step-by-step procedure. Step 1. Draw the front view and plan view of the truncated cylinder. The front view shows the cylinder outline with the cutting plane as a sloping line. The plan view shows the base circle. Step 2. In the plan view, divide the base circle into 12 equal parts, 30 degrees each, and number the division points 1 to 12 going clockwise. Step 3. Project each numbered point vertically up to the baseline of the front view. From the base, erect vertical generator lines up to the cutting plane line. Mark the height of each generator where it meets the cutting plane, call these heights H1, H2, H3 through H12. Step 4. Draw the stretch-out line. Calculate the circumference as pi times the diameter. Draw a horizontal line of this length. Divide it into 12 equal parts, each part equals the circumference divided by 12, and label the divisions 1, 2, 3 through 12, and 1 again at the far end to close the development. Step 5. At each numbered division point on the stretch-out line, erect a vertical line and mark off the corresponding height taken from the front view. At division 1, mark H1, at division 2, mark H2, and so on. Step 6. Join all 12 top points with a smooth curve. This curve is a sinusoidal wave, it rises and falls smoothly. Draw it using a French curve or a flexible ruler. Step 7. At the base, attach the true shape of the base circle, a circle of the correct diameter, at one end of the development. Attach the true shape of the cut ellipse at the curved top. Mark all fold lines as chain dash lines. Label the development with its title and dimensions. When the cutting plane passes through the top of the cylinder at the highest point and the lowest point on opposite sides, the development curve is a full sine wave. It starts at height H1 at the highest point, descends smoothly to H7 at the lowest point, and rises back to H1 at the end. If the cutting plane is very steep, the difference between H1 and H7 is large and the curve is very wavy. If the cutting plane is nearly horizontal, the difference is small and the curve is nearly flat. To achieve accuracy, consider using more than 12 generators. 16 or even 24 generators give a more accurate curve, especially for steep cuts. However, 12 is sufficient for WAEC examinations and is the standard expected. One common error is to draw the stretch-out line shorter than the true circumference. Always calculate pi times diameter carefully. If the diameter is 60 mm, the circumference is 3.142 times 60, which equals 188.5 mm. Mark this accurately on your drawing sheet. Another common error is to connect the top points with straight lines rather than a smooth curve. The curve must be smooth, no corners or flat sections. A practical application of cylinder development is the pipe elbow, a bent pipe connecting two sections of pipework at an angle. A pipe elbow at 90 degrees can be made from two truncated cylinders mitered together. The miter cut is the inclined cutting plane. To make a 90-degree elbow from two equal cylinder pieces, cut each cylinder at 45 degrees. The development of each truncated cylinder piece gives the pattern for cutting the sheet metal. Welding or rolling along the development seam produces the elbow. In HVAC engineering, engineers make complex duct systems using development of cylinders and cones to ensure precise fit-up. In Nigeria, skilled sheet metal fabricators use hand-drawn developments or computer-generated flat patterns to cut duct sections for air conditioning systems in large commercial buildings. To summarize, the development of a truncated cylinder begins with the stretch-out line equal to the circumference, pi times diameter. Divide into 12 equal parts. Project the heights of 12 generators from the front view. At each division point on the stretch-out line, mark the corresponding height. Join the top points with a smooth sinusoidal curve. Add base circle and cut ellipse through shapes at the ends. Mark fold lines. Label fully with dimensions. The key differences from prism development: the stretch-out length is the circumference rather than the perimeter, and the top edge is a smooth curve rather than straight lines. Practice plotting at least 5 different truncated cylinder developments before the WAEC examination. Speed and accuracy come from repetition.